Welcome to this tutorial on network modeling that is part of Succinct's video series on socio-environmental modeling. This video introduces methods and analytical techniques associated with network modeling. For a more basic introduction to networks, please see the Succinct resources for the video by Philip Stanisenko, Introduction to Socio-Ecological Networks, and the 3 lessons by Margaret Palmer and Heidi Scott, Network Methods to Understand Complex Systems. Remember, socio-environmental systems are complex adaptive systems and difficult to describe in ways that convey their components and interactions. That's where networks are relevant. Think of them as simpler depictions of the structure of complex systems. In this video, we'll discuss how a socio-environmental system might be represented as a network in many different ways. The tutorial covers 7 things. We start with motivation, then move to some basic terms and concepts, and how networks can be represented. Next, we describe a few of the measures that can be used to understand network structure. We provide some examples of the use of networks by socio-environmental researchers before summarizing and reviewing the steps involved in their use. Okay, so motivation. Why is network analysis so useful? The answer is related to what is sometimes described as the paradigm of network science. Networks, in their analysis, provide a powerful way to study complex systems. Network structure of a system, its composition and properties, reveals a great deal about its function, meaning its likely dynamics. By functions, we mean, for example, a system's ability to withstand a targeted attack, or a failure, say, due to an environmental or economic disaster. Another example is a network's ability to efficiently distribute information, which is known under a variety of names, including contagion, spread, or peer effects, and includes familiar examples like disease transmission, propagation of rumors, or also invasive species. The powerful abstraction of network science simplifies the study of complex systems, assuming a certain class of underlying dynamics, or, to use the term we have used in other socio-environmental tutorials, system behaviors. The abstraction also provides a way to use statistics and mathematics to quantify structure and thus function, and networks open up new ways to model system dynamics. Throughout the talk, we'll be using examples to illustrate 3 major uses of network modeling to study socio-environmental systems. First, they can quantify changes in system structure over time or space. Second, they can be used to identify critical system components for control or management, for example, to allocate resources or control invasive species. And third, they are useful in predicting responses to that management or responses to perturbation, say, when oil spills impact fishing communities. Let's now cover a few basics, mostly terminology. The entities in a network are the nodes. These could be people in a social network, institutions, ecosystem types, or any component in a socio-environmental system, such as species in an ecological network. The relationships, such as those between multiple plants that are connected by pollinators, are called edges or links. Edges can also be called bonds, and nodes can also be called vertices. For a directed network, the edges have a direction. For example, here there is a link from node A to B, and from node C to A. We say node A has an outlink to B and an inlink from C. Here is another directed network. Note that removal of a node can disconnect networks, and when that is the case, they are referred to as articulation points. So, in this simplified network, losing node A, perhaps a farming group in a social network, can disrupt the system of connections. It's worth noting that in studying socio-environmental networks, researcher Peter Sales refers to network articulation in terms of fully articulated, when components and their relationships are fully specified. He distinguishes these from representations in which the social, blue nodes, and environmental, green nodes, are only partially specified. When they are considered jointly, he calls these non-articulated. He believes fully articulated are the most appropriate because socio-environmental systems are shaped by both social and environmental connections. We bring this up since we're focused here on such interactions, but note that more generally, however, network terminology varies a lot by disciplines. Okay, so shifting to a few brief comments on the origin and mathematics of networks. Network science comes from graph theory, a branch of mathematics. The two are not the same, but use the same underlying mathematical theory. Graph theory doesn't refer to data graphs, like line graphs you may be very familiar with, but it does refer to groups of things that are connected. It focuses on providing theories and developing algorithms for abstract networks. Network science is more applied than graph theory and focuses on techniques for analyzing structures in networks. It quantifies relationships using real-world data and is very useful for focusing on complex systems. Measures that represent attributes of a network structure are powerful tools for quantifying network features like the level of connectivity. They can be statistical or more complicated, and as I indicated, the underlying mathematics comes from graph theory. The math involves adjacency matrices. Here, rows and columns represent nodes, and each matrix entry represents the link between its column and row. Entries can be binary, zeros and ones, or other quantities defining the strength of the link. A matrix can represent both in and out links. For example, the lower triangle of the matrix can be used to represent in links from the rows to the columns, and the upper triangle out links from the columns to the rows. Critically, all the network and node level statistics or properties we will describe later can be computed from an adjacency matrix. Even socio-environmental or other complex networks like the one illustrated in this paper by Orjan Boden and colleagues could be analyzed mathematically. Constructing the matrix would be more complicated, but there is software to help. Moving on, let's consider some different ways to represent networks that convey more information about their complexity, something common for socio-environmental networks like the Boden example. So far, we've mostly seen representations of simple networks like this one. But other representations include those called multiplex, composite, and multi-layer. Because network terminology is used differently by different people or disciplines, just keep in mind such terms just refer to how we can conceptualize and draw networks. Perhaps we want to show that the network is of farmers that communicate and are linked by social relationships, but later we find out that some of the farmers are actually sharing markets. These are now shown as blue links to distinguish them. So, we've added data about the characteristics of each farmer's relationship that are of two types. When the nodes are all the same, like how all of these are farmers, but their relationships differ as depicted here, these may be called multiplex networks. But perhaps the network also includes farmers who do and do not use conservation tillage practices, so the nodes actually differ. Farmers using no-till are now indicated by green nodes, and those still using tillage, all the rest, by blue nodes. Some scholars call these composite networks, but this isn't a very commonly used term. Depending on the field of study, it can mean a network with all the same nodes and different types of interactions, but in other fields it may simply mean a network with different subnetworks. Note this network is depicted as a single layer or level. But another way to represent networks that is better for socio-environmental systems is using multiple layers, as in this new network representation. Now, different types of nodes and their relationships are in different layers. For example, layers may be used to separate social and environmental nodes, each with their own intra-layer links. Sometimes the layers are called subnetworks or subgraphs. As an example of a multi-layered socio-environmental network, the green environmental layer here may represent different species of birds, only some of which share the same type of habitats, while the social layer may represent a network of bird watchers with different preferences for the species they seek out. Note that the interlayer links represent the socio-environmental links in this representation. This new image illustrates a two-layer network that is unbalanced. There are different numbers of nodes in the layers. This type of representation formalizes heterogeneity in types of links. Note that networks can have many layers, sometimes dozens or more. Here is a three-layer network. There is a human or social level, with nodes and links representing actors and relationships, and another social layer with nodes and links representing governing institutions and their interactions. Then there is an ecological or environmental level, with ecological nodes and links. The ecological nodes could be habitat patches, and the links connections via dispersal. Between layer links could represent human links to their governing institutions, or human links to ecosystems they rely on for resources, for example, ecosystem service flows. In short, multi-layer representations allow one to show many relationships, and it's worth noting again that these can involve many layers, each with complicated interactions within. But how do we measure the structure of such networks, and why is network structure of interest? Regardless of the type of network or the study domain, measurements of network structure are all linked to the central paradigm of network science, namely, that structure is related to function. It can tell you a lot about a system that has many interacting components, like, for example, which node is most influential, how connected is one network compared to another, and is the network robust to losses in connectivity or a component. Structure of a network is analogous to something's shape and complexity, and there are a number of measures to describe it. Network structure can be focused on the node level or at the level of a whole network. Let's look at some examples of network measures. See how different these three networks are. They are from a study on farmer networks to promote biodiversity agriculture. The first one has lots of connections and no one node really dominates, while the one that is rightmost is a modular network because there are subgroups of nodes that preferentially interact with one another. The middle network is centralized because there are a few nodes with lots more connections than the other nodes. These three networks can be characterized using network measures that identify patterns such as connectivity, modularity, and centrality. All such measures are based on statistics and matrix mathematics as mentioned earlier. Let's talk about a few of these measures. Connectivity can describe how connected a single node is or a whole network. This is a fully connected network. Every node has a connection to all other nodes. But connectivity can be much more complex and can be evaluated in lots of different ways. In a network where connections are high, but extremely centralized like this, a single failure of the most important node, here the middle node, can cause major disruptions. The measure's centrality is related to the number of connections that a node has. The more they have, the more central they are to network function. Here, two nodes qualify because each has 4 connections. However, if you lost the purple node, look at what it does to the network. Now there are 2 more isolated networks. So actually, one was more central to network function than the other because it played an important role in overall network connectivity. There are many other types of node-level measures that focus on the importance of a node. Examples include node degree, which is just the number of connections a node has. Others are betweenness and closeness centrality, which are related in different ways to how close nodes are to other nodes in terms of links. Page rank is a measure of how many valuable links come to a node. In other words, its in-link connections. Homophily refers to connections being more common among nodes that are similar. Many network measures can be applied at the level of a whole network. For example, cohesive networks have many ties that are widely distributed. These networks are hard to separate. Here's a very different network that looks more like a flowchart. This is a hierarchical network, where there are clear paths of connections. Okay, let's move on to give some specific examples of socio-environmental studies and how they are used to understand network dynamics. Jessica Gebhardt and colleagues studied the global seafood trade network, gathering lots of data from various sources. They asked how robust this network is to disruptions due to environmental disasters, such as hurricanes, or to stock collapses that resulted in low or no catches of seafood in a region. Would the disruption propagate through the network and cause food insecurity elsewhere? The more connections in the network, the more the effects cascade. With their network model, the authors experimented with decreasing the strength of connections from a country that exports a lot of seafood, say Norway or Vietnam. This caused a food shock in some importing countries. That is, the network was not robust to losses for countries that relied heavily on imports. In another study, also focusing on network robustness in the face of perturbations, Emma Fuller and colleagues measured the connectivity of fisheries on the US West Coast based on how many species in common vessels targeted. Nodes were the fisheries, or species, and the links between them were proportional to the number of vessels that fished each of them. In other words, links were weighted as indicated here by the different link widths. They used a simple equation to measure link weight, or resource sharing, based on which fishery species were caught between all combinations of two vessels. They also used a simple measure of connectivity that took into account the evenness with which vessels relied on different species for income. Betweenness centrality was used to determine how important fisheries were in networks. They showed that some of the vessels were generalists fishing on many species. Vessels with more diversified fishing portfolios were far more able to cope with loss or decline in a particular species. This analysis allowed the authors to investigate risks and the capacity to adapt to change, both of which can inform governance of natural resources. In a study of Andean herds and people, Marcos Easdale studied their seasonal movement between mountain and pasture sites. The movements allow them to avoid dangerous snowstorms in the highland winters. Some of the sites are communally managed by different households, and the movements by different households represent exchange of matter and water between summer and winter lands. Different grazing sites are the nodes, and there were over 1,000 linked by the movement of people and herds. The authors identified subnetworks within the global system such that most sites were only connected to one other site, forming a dyad. Some sites were connected to two others, forming a triad, and some subnetworks were complex. Network analysis allowed the authors to reveal several things. First, this was actually a highly fragmented socio-environmental system composed of many smaller networks. Second, the more complex subnetworks had mostly star-like topologies and relied heavily on a central site. In other words, they showed high betweenness, indicating high vulnerability, as was the case for the last two studies we described. Third, in terms of the potential for cascading effects across the larger region if something happens to one site, say, because a herder allowed overgrazing, the large number of dyads and triads provided some isolation, thus reducing the likelihood of dangerous cascading effects, sometimes called contagion, as with disease transmission. Therefore, while the more complex herder networks will need careful management or conservation of key sites to protect their users, the rest of the subnetworks are unlikely to suffer from losses. Focusing on more positive issues, like how understanding network science can help us sustain socio-environmental systems, research by Émile Delange and colleagues identifies levers for promoting behavior change to better support conservation actions. Since social influence is important to such change, people look around to see if and how change benefits others who they think are credible. If early adopters are socially linked to others, there can be positive cascading effects with behavior change spreading among connected people. For networks with high levels of homophily, collective conservation actions are more likely. Interestingly, the authors also cite work suggesting that more heterophilous networks with more different individuals and sparser ties are more open to innovations, but less likely to coordinate. Not surprisingly, those individuals, that is, nodes, with the highest centrality scores are more likely to be influential. The authors summarize the ways networks could be used to simulate change, including targeting communication leaders or an incubator neighborhood, recruiting opinion leaders, connecting subgroups, or connecting peers for learning and reinforcement. It is even possible to indirectly reach target audiences by inducing multi-step communication flows. Okay, to wrap up, we remind you of the key points we covered. First and foremost, networks are useful for quantifying changes in the structure of socio-environmental systems that influence their dynamics. Terminology can vary by disciplines, like links can be called edges, and there are multiple ways to represent networks to convey the most information. Network analysis makes use of standard mathematics and statistics and is useful for identifying crucial controlling components and predicting responses to things like shocks and changes in management. Network analysis is now used extensively to understand and identify management paths for socio-environmental systems. Now let me briefly summarize an overall recipe behind most of the network-based analyses that we have seen. First, develop a network representation of your SE system. Second, focus on your question or goal because this will guide the type of network analysis you want to do. Third, choose an outcome variable of interest that is reflected in network structure. Fourth, for the question you are interested in, identify which network attributes you are most interested in. Is it connectivity, centrality, Homophily? Remember, these can be good or bad. Fifth, quantify network structure using summary statistics, global or node level, depending on goal. We hope you found this video tutorial useful. Thanks for watching.